Hello again, everybody. Today we're going to talk about turbulent flow. Label is Chapter 9 in the textbook that we use for the undergraduate class, which focuses on turbulent flow. In the last video, we talked about how to analyze laminar flow, which gave rise to these sort of differential forms that we use to analyze microscopic fluid properties, microscopic flow profiles, and how we eventually derive the Navier-Stokes equations and use those to solve problems. In this chapter, we're going to switch from laminar flow to talk about turbulent flow because, as was mentioned before, turbulent flow is really what's used in a lot of chemical engineering processes. Unfortunately, how to analyze turbulent flow is much more difficult and still an area of active research, how to model turbulent flow. There's not many analytical solutions for turbulent flow. So in this class, we're going to discuss a lot of the assumptions and a lot of the models that we're going to make for turbulent flow, and then describe a couple examples for how we might use those problems. So in turbulent flow, what happens is, rather in laminar flow, where you've got these nice, smooth profiles, is you've got these big eddies and big whirls, and these big whirls turn into smaller ones, and they eventually dissipate into sort of the normal flow. And so analyzing these sort of chaotic profiles is rather difficult, and that'll be the focus of this class. So what about turbulent flow? So when you have high Reynolds numbers, as was talked about in the previous videos for fluid mechanics, you have, once you get past the sort of laminar and the transition region, you have turbulent flow, so high Reynolds numbers. And in this case, you'll have, the flow will be sort of, like I mentioned, these whirls, these eddies will be moving all along. In this case, imagine this cross-section of a pipe. Whereas at the surface, because of the no-slip condition, you'll have these very thin laminar boundary layers. And we're not going to focus a ton on the boundary layers themselves, but these are very important for chemical engineering. And because the reason we run turbulent flow most often is because, as you can imagine, we want mixing. So while analyzing the flow profiles are much harder with turbulent flow than laminar flow, the actual process is much better because we get a lot of mixing. So if you want to talk about having better temperature, reducing temperature gradients and having better heat transfer, mass transfer for reactions, things like this, you want a lot of mixing. And so turbulent flow is great for that. But at the surface, you'll have this laminar flow. And usually this laminar flow will control a lot of this mass and heat, because once you get in the tubular region, you have a lot of mixing. So you don't have to worry so much about these different gradients developing. But in the laminar region, you'll have the majority of the barrier for the different transport processes. So it's important that we have, understand there is, even though it's very thin usually, this laminar sublayer and then the turbulent flow out here. We're going to talk about how we might develop what's called a universal flow profile that combines the laminar flow and the turbulent flow, and that'll be the focus of today's video. So first, talking about what turbulent flow looks like, we're going to talk about, the flow has what I call these eddies. There's this swirling fluid. So the fluid swirls, and you have a reverse current created when fluid flows past an obstacle, or just when it's flowing really quickly through, like for a pipe, for example. And usually what happens is you'll get these large eddies formed at the expense of the pressure energy. So that pressure energy is what's driving the flow, it's driving the high velocity. You'll get these large eddies. And oftentimes in pipes, some of these eddies can be as large as the pipe diameter. So you can imagine if you've got a pipe, you've got some of these big swirls are happening almost the same size as the pipe diameter. But the larger ones are quite unstable. They usually break apart, and then you'll find these medium-sized eddies, which will swirl a bit more. And then as these break down, they'll make it even smaller, and so on and so forth, until eventually these small little eddies, which have the same amount of mechanical energy as large eddies, they'll dissipate by the viscous forces, and all that mechanical energy will turn into heat. So how do we characterize these eddies? You can imagine before with the laminar flow, it was relatively easy to look at a flow profile and to sort of say, okay, if the flow is going, velocity is in the x direction, for example, it's only going to vary in the y direction. We have these nice flow profiles that we know exactly, okay, if you're at this position in y, your velocity in x is going to be this. You've got these nice, really straightforward equations to analyze this. Now, how do we use that when we've got fluid swirling? So we've got velocity x, we've got velocity in the y direction, we've got velocity in the z direction. It's moving and it's relatively chaotic. So we're going to use what are called time average quantities to sort of start to derive these universal flow profiles. And the idea of these time average quantities is that we're going to take a velocity in x, which is it's variable. And so if you look at this graph down here, you can imagine this line here is going to be at any given time. So time is going to be here on the x-axis. Your velocity in the x direction is going to be higher, then it's going to be lower, then it's going to be really low, then it's going to spike back up. So you're going to have this huge fluctuation in the velocity in the x direction. Laminar flow, it's flat, it's one value. So what we're going to do is we're going to say, okay, you know what? The velocity in the x direction is just going to be equal to the average velocity, which is this blue line. We're going to denote that here by this Vx with the bar over the top. This is the average velocity plus the fluctuation from that average. So right here, you'd have a large fluctuation from the average. Right here, you have negative fluctuation, smaller fluctuations. So at any given point in time, you're going to have some sort of fluctuation away from the mean velocity. Now, by definition, because if you take this profile here, you get the average, and then you're looking at the distance away that each point is from the average. By definition, if you sum all those up, they're going to be equal to 0. That's sort of the definition of what an average is. So, but if you take, even though the sum is 0, the intensity, if you take that and you take the average of these fluctuations and square them, and then take the square root, this is known as a root mean square, that's going to give you an idea of how intense the variations are. So if you've got smaller fluctuations, right, this root mean squares from the mean is going to be smaller. If you've got much larger ones, this is going to be higher. And so we're going to note this is with this here. That's going to be the root mean square, or the intensity of these fluctuations. We can also do the same thing with pressure, although we're mostly going to be dealing with velocity in this class, but we have the same thing with pressure, where the pressure is going to be fluctuating too as a result of this. And so you have the pressure is going to be equal to your average pressure plus some sort of fluctuation away from that average. So if we look at the momentum balance, and we're going to convert this from the momentum balance, and we're going to add these time averages to the momentum balance. So we've got our average here velocities, our average pressure, and then we've got our average shear stress, or average normal stresses all over here. And we're going to add this term here, which is going to be known as these Reynolds stresses, which are derived from the fluctuations due to turbulence. So if you remember our last derivation, we did the Navier-Stokes equations, we were just worried about, okay, we have a differentially small piece of fluid, and remember that's a convective derivative, so it's moving with the fluid. And we just looked at the stresses that were on that little sort of volume of fluid. Well, now we're going to say we have the stresses that are doing the volume of fluid just like before, but now we also have sort of fluctuations as that fluid is experiencing turbulence, and stuff's moving in and moving out as a result of the turbulent flow. So in most cases of turbulence, the Reynolds stresses, which is the due to the fluctuations of turbulence, is much larger than the viscous shear stresses. So the viscous terms that we used before in the laminar flow problems, we're going to ignore them, and we're only going to really focus on these new Reynolds stresses that are due to the turbulence. And we can do similar momentum balances for the x and the z direction, or the y and the z direction. This is the momentum balance in the x. If you remember Navier-Stokes, we had x direction balance, y direction, and z direction. So this is just the x direction, and we can do the same thing for the other two. All right, so let's look at what are these Reynolds stresses. So where do they come from, and how does it relate to the equation we just showed? So if you imagine the Reynolds stresses come from, so imagine a piece of fluid volume, so it's going to be this sort of hockey puck looking piece of fluid here, and it's going to jump in the y direction as a result of an eddy, right? So you've got this volume of fluid, it gets caught in an eddy, and it's going to jump up in the y direction, it's going to cross this plane x here. So, right, because of the eddy, it crosses this plane right here. So the momentum transfer in the y direction, the fact that it's moving up in the y direction, is going to result in a shear stress, which is going to be equal to, the turbulent shear stress, which is going to be equal to these fluctuations terms that we just showed, the fluctuation of the x, fluctuation of the y. The major problem is, so okay, this is what we mentioned in the last slide. So we just defined it here as this tau yx turbulence right here. The problem is we can't really measure or predict what this is with the equation that we used below. Okay, so we kind of just define where these Reynolds stresses are coming from, but we're not really any closer to coming up with a usable equation. So we're going to use what's called Prandtl's mixing length theory. And so, okay, so now we're going to imagine particles that are moving from the bottom plane, B, right here, up to this plane, X, that we talked about before, or from the top plane, A, down to X. So fluid, jumping up, fluid jumping down. The fluid would be moving in the B direction up due to a fluctuation, right, in Y, or moving down due to a negative, fluctuation in the negative direction, down from A here. So since these distances are short, we're going to assume that the velocities here are going to be a linear flow profile, because we're going to talk about small mixing lengths here. So the mixing length here is going to be this lambda right here. It's the distance that you're going from here up to here, the distance from down here, right here, and it's going to be moving in this fluctuation right here. So if you mix all this, you're going to have the velocity is going to be equal to, again, this is your average velocity in the X, minus the rate times which again is the velocity here, the rate times the distance that it has to travel. So this is how we're going to define this, this parameter here now. So if we now, okay, we have a term here that's talking about the velocity. So now we're going to go from velocity to momentum. So the momentum going from B up to this X is going to be the fluctuation right here, times, again, a lot of the using density and velocity to get our momentum right here. So this is just converting the equation we had before to some sort of momentum equation right here. So now if we take momentum and we do what we did before, right, we take a time average momentum. Because just like before, just like our velocities are fluctuating, our momentum is also going to be fluctuating. So we're going to take time average momentum, and that's going to have to do here within time averages and fluctuations. And so we're going to derive this new expression here. Again, this is going to have a lot of these different terms here, so just bear with me as we work through until we get to sort of a usable equation. All right. So, excuse me. So again, we have this time average momentum right here, which we derive this new term right here. We're going to have the eddy kinematic viscosity, and we're going to redefine it as just from this term here. So this value is going to be defined as sort of these fluctuations times the lengths that the fluctuations are traveling. And we can redefine it in terms of R, where it's going to be a correlation coefficient. So in correlation coefficients, a lot of this is going to be experimental. So we're going to have this correlation coefficient, and we're going to have now, instead of the sort of average values, we're going to have the root mean squared, the intensities of these fluctuations, the intensities of the fluctuations here, and the length as well. So if we take this, again, empirically, it's been found that the velocity disturbances in the X and the Y directions are proportional. So meaning if something is fluctuating very high intensity in the X direction, it's also going to be fluctuating in the Y direction proportionally. So not necessarily the exact same, but it's going to be proportional. So while it might be fluctuating twice as much in the X as it is in the Y, if you then double the X, it will also double the Y. So that's what it means by they're proportional to each other. So we can relate the Y fluctuations, or the intensities of the Y fluctuations and X fluctuations with this additional correlation coefficient of beta. So again, we're adding more and more correlation coefficients for sort of experimental work later. So we introduced this term here. If you look, so what we did is we converted basically the Y fluctuation here into the X fluctuation. So that's what we termed here. So now what we're going to do is we're going to say, okay, we've got rid of the fluctuations Y. We're only dealing with fluctuations in X because we're analyzing the velocity in the X direction. So we now are going to define here this fluctuation in X, the sort of the root mean square fluctuation, based on the cause of the fluctuation. And what's the cause of the fluctuation? Where it's going to be due to the changes in the velocities between the two planes, meaning you've got some velocity up here, and then you're moving down here, and you're going to have a different velocity. Again, introduce another constant, alpha, which is just going to be equal to this. It's going to be, equal to sort of the average change in velocity as you go from up here to down here, or down here to up here, right? That's the rate of change of the average velocity in x with respect to y. And it's going to be equal to, again, the intensity of the fluctuations of the distances with some correlation coefficient here. So we're going to replace this into this equation here and add yet another correlation coefficient here. So now we've got coefficient, 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 two of these fluctuations at the mixing length here, and then we've got our velocity profile for the average velocity in the x direction with respect to y. Okay, if we go through and plug everything all in, so this was where we started, right? The time average of momentum. We ended up here with this, was our definition here of this parameter. And so we have this equation right here. We're going to define a new term, which is L here, which is known as the Prandtl's mixing length. So this is going to be basically we're going to lump in a lot of those correlation coefficients and experimental parameters together and call it the Prandtl mixing length. And this mixing length is very important. You're going to use this parameter in mass transfer, heat transfer, momentum balance, basically to help quantify different rates of transport in turbulent flow. So this was the point, to group all of these different correlation coefficients into one parameter, which is L here. Okay, so we haven't, we've sort of reshuffled things and reorganized equations, but we haven't really gotten yet to real systems. So how do we find L, or the mixing length, in a real system, and how would we correlate it to momentum? So that's what we're going to talk about next here. So as was mentioned before, if we're going to assume that the laminar viscous shear stresses are small, and it's mostly these turbulent Reynolds stresses are what's dominating, that would be, the laminar ones here and the turbulent ones here. We're going to say, hey, you know what? These are very, very small. These are much larger. So we're going to say, both of these together are really mostly equal to just the turbulent stresses. So then we get the turbulent stresses for yx here is just equal to y times our pressure variation with respect to x. If we go ahead and plug in what we just derived here in the last slides for this side of the equation, we end up with this equation here. And now this right here, y dp dx, this is going to be the shear stress at the wall. So if you're talking about a plate, it would be the shear stress at the wall. We're going to get tau w, and we'll come to this in the examples later. In pipes, we're going to use cylindrical coordinates, so it's going to look similar, except because of cylindrical coordinates versus Cartesian coordinates, we're going to have the tau at the wall as a function of this here, r over radius over 2 dp dz, okay, which just basically adjusts this. Instead of y, you have r over 2. Again, that has to do with switching from Cartesian to cylindrical coordinates. Why is this important? Why did we make this change? Well, because pressure drops are relatively easy to measure along a pipe or a plate. So just like in some of the examples you might have done in the previous lectures in chapters 3 and 4, pressure drops are a parameter that you can experimentally measure, right? You put a pressure gauge at point 1, a pressure gauge at point 2, and you can get relatively easy experimental value for pressure drops. So by converting something like this, or like this, which has mixing length and all these things are a little bit harder to measure directly, we've converted this into something that you can measure directly, which is this pressure drop over the length of the pipe or over the length of the plates here in this case. Additionally, you can measure velocities as a function of y or r as well. It might not be as easy as pressure drop, but you can do it. So now we've got this in terms of parameters. You can measure average velocities as a function of r, average velocities as a function of y. And so we're starting to be able to get these terms into something that we can actually measure experimentally. Okay, so we're going to basically switch to empirical equations, and this is very similar to what you did when you're dealing with the friction chapters in fluid mechanics. A lot of this stuff, there's not a direct analytical solution. So we basically come up with models and use empirical equations and then do experiments to try to fit these equations. And so what's been found by the pressure and velocities in pipes, the Prandtl's mixing length, which is L over A. So A would be, A here is the radius of the pipe. So the Prandtl mixing length over the radius of the pipe is equal to this empirical equation here, which is just a function of where you are divided by the total radius of the pipe. And the eddy kinematic viscosity can then be calculated using this other empirical relationship here. If you go back, to some of the friction equations, these start to look a lot like some of the friction equations that were used to analyze friction back in the macro fluid mechanics. Okay, so moving on to, we kind of have a way to figure out what the mixing length is, using these equations we mentioned before. So Prandtl's hypothesis was that the mixing length increased proportionally with the distance from the pipe wall or the plate. Now that should hopefully make sense. What that means is, right, as you move away from the wall or the plate, the pipe wall or the plate, where the velocity will be zero, right? As you move away, the velocity is going to be increasing as you go towards the center of the pipe or between the two plates. The velocities are going to increase, and the mixing length will also increase proportionally as you move away. And again, the reasoning for this is that the eddies will have more freedom to move away from the wall. When they're closer to the wall, they're kept small because you have that boundary. And as you get more towards the middle, they're able to move much more freely. You can have much bigger mixing lengths. So if we take this value here, which is just, again, it's linear. So basically you have some slope times the distance from the wall is going to be equal to your mixing length. And you can plug this into the equation we had before. So if we take this now and we integrate it to solve for Vz, you end up with this equation here, which is just your average velocity in the z direction, we're talking about a pipe, is equal to 1 over the slope that we said here, which was how fast proportionally the mixing length increases as you move away from the wall. Shear stress of the wall over viscosity, natural log of your distance away from the wall, plus some sort of constant. So this is the integration of this equation here. So what's interesting about this equation is that originally people were using this as an approximation to study the fluid profile near the pipe wall. So think, okay, not necessarily in the main turbulent core, but near to the pipe wall. And a lot of the assumptions that were made are known to be wrong, but somehow the error in them seems to cancel out, and it actually can be used to estimate the velocity profile in the central region of the pipe as well. So it actually ended up working out quite well. And we're going to use the form of this equation here to sort of help develop our universal flow profile. So again, based on this derivation here, we're going to develop a university profile. So it's true for all smooth pipes. Now, how could you possibly, we just talked about how different turbulent flow is from laminar flow. So how can we develop a flow profile that describes everything? And really the trick here is to use dimensionless groups like before. So you'll find this comes up quite often in different chemical engineering classes, is you're going to develop a dimensionless group that's going to allow you to sort of define how a system works independently of the size or the shape or anything like this. So in this case for pipes, we're going to define dimensionless distance from the wall, which is going to be the sort of plus here, y plus. And that's going to be equal to the actual distance times the square root of the shear stress of the wall over density here. This is also, we'll be using this a lot down the line. So you'll see this square root tau w over p will come up a lot. And then divided by the kinematic viscosity. If you use this and you go through the math, this will give you a dimensionless number. There will be no units left over. And so that's going to be our dimensionless distance. We can also do dimensionless velocity here. So dimensionless velocity in the z direction is going to be your average velocity in the z direction and divided by the square root of the shear stress of the wall over density. So if we rewrite the equation above using these numbers here, you end up with the dimensionless velocity is equal to some constant b, natural log dimensionless distance plus a. Now, experimentally, when they go in and they calculated a bunch of experiments using these forms, they found that b is equal to 2.5 and a is equal to 5.5. So now, if we plug in 2.5 and 5.5, we now have a dimensionless flow profile that describes the flow in the turbulent region of the pipe. So how do we know where the turbulent region is? Well, when y plus, or the distance from the pipe wall, is greater than the dimensionless distance is greater than 30. So again, this takes into account this, the how big the pipe is, how small the pipe is, how it doesn't really matter. You can scale it dimensionlessly to say, hey, when our dimensionless distance is greater than 30, we're going to be using this equation here, which is towards the middle of the pipe. And you're going to get a dimensionless velocity. Now you can convert your dimensionless velocity then back to real average velocity by using this definition here. So you're going to solve for this, and you can back out what your real velocity is. So we'll do it in a couple examples, but the idea is you use this, your real distances, to calculate your dimensionless distance. Your dimensionless distance will plug in to this equation here to get your dimensionless velocity, and then you'll go back out using this equation to get your real velocity. So you use these dimensionless equations as a means to go from real space into this sort of dimensionless, and then go into real velocity. Now, we just mentioned that this is true in the sort of the turbulent core, but not really true close to the wall. So when you're close to the wall in the laminar sublayer, you can actually approximate the equation like this, which is just your dimensionless velocity is equal to your dimensionless distance. So when your y plus, your dimensionless y is less than 5, your dimensionless distance and your dimensionless velocity are going to be the same. So when you're in the laminar sublayer right close to the wall, this is the equation you're going to use. And then you're going to have a buffer region between 5 and 30, where empirically this is the equation that was determined. So if we can convert this velocity profile to not just calculate what our average velocity right here, our average ZM is right here, or sorry, our average VZ right here, but we can also use it to look at the mean velocity, the entire mean velocity through the pipe, which would be VZ, we're going to call VZM. So if we take this equation here, which gives us our time average velocity as a function of R, and we can integrate this across the entire area. So this is just basically our volumetric flow rate over area is equal to integrating the flux, which is the velocity through that cross-sectional area. We can derive a form for this is the mean velocity through the entire pipe. Or if you remember the earlier chapters where you're doing macroscopic fluid mechanics, this would just be your mean velocity through the pipe. We can calculate that using this equation here. So we're not going to go through this derivation in the interest of time, but if you were to do this, you would end up calculating this equation here, which looks very similar to the other equation, except now we still have right here 2.25 for B, but instead of 5.5, we have 1.75 here for this constant. This term here looks like Reynolds number. This term here looks like your friction factor. So it really relates to a lot of the friction factor equations that were used earlier in the chapter for macromolecular, or not macro, fluid mechanics. So based on this university velocity profile right here, to calculate your mean velocity through the pipe, the friction factor here and the Reynolds number can be related to this equation here, which is very similar to what was discussed in chapter 3 for smooth pipes. If you remember chapter 3, you'd use Reynolds number, you'd look at the chart for friction factor, and you'd use them to calculate each other. This equation here is very similar if you solve for Reynolds number friction factor. Okay, if you kind of rearrange this a little bit, you can also get this equation right here, which is just, again, rearranging this equation, but now we're plugging in this, which is, should look somewhat familiar. This is the dimensionless distance, but instead of Y, we've replaced it with A, where A is the entire length of, the entire radius of the pipe. So instead of Y right here, we're just substituting that with A. So instead of going from the center of the pipe, or the pipe wall down here, going up to the middle of the pipe, we're going from the pipe wall and we're integrating over the entire radius. And so we're just using A here instead of different values for Y. But this here is the equation you'd use to calculate your mean velocity through the entire pipe. So just like before, we have now this equation here that can relate dimensionless mean velocity. Again, using this term here, which we call friction velocity. This comes up over and over again, our tau at the wall over density. It relates our real mean velocity to this dimensionless mean velocity. So we can calculate dimensionless mean velocity by using this equation here, 2.5 ln a plus. This right here is a plus. You can go back and look at the equation for dimensionless distance, going from y plus to y, and you'll see that these are the same thing, but we're using a, again, the total radius of the pipe instead of y. So this is how we can go back and forth between dimensionless mean velocity and dimensional and real mean velocity. So very similar to instead of going from VZM when we talked about VZ was the same thing, except this was y plus and this was 5.5 instead of 1.75. And we'll see how we handle that in the examples later. Okay, so going back to this equation here, we talked about, we now have these universal flow profiles here. And we're having three different regions. One, where you're far enough away from the wall, where you have basically the turbulent core here. One where you're right up against the wall, where it's pretty much the laminar sublayer, which is this, and then a buffer region between the two, which can be described here. Another approach is to just say, you know what, we're going to use two regions. Rather than having this buffer region, we're going to just have the turbulent core and the laminar subregion. We're just going to get rid of this buffer region. So this is known as a three-piece model. When we get rid of this, it's known as the two-piece model. But you'll notice that there'll be a bit of a gap. So we actually adjust the cutoffs here when we're using the two-piece model. So for the two-piece model, if we just say, okay, let's set these equations together. When will this equation equal this equation? And then we solve for the y plus to give us the y value when the two-piece model would be equal. So if you set the dimensionless velocity to the dimensionless distance, which we also know is equal to this, if you set all this together and you solve them, you'll find that your dimensionless distance will be equal to 11.6. So if you're using the two-piece model now, the cutoff here is 11.6. So anything greater than 11.6, you're going to be using this equation here. VZ plus equals 2.5 ln y plus 5.5 for anything greater than 11.6. And the laminar sublayer will be anything less than 11.6. And there you'll just have VZ plus equals y plus. So here's another way of deriving this with the two-piece model. And usually in a problem, you'll either choose two-piece or three-piece, or the problem statement will say, solve this problem using the two-piece model, solve this problem using the three-piece model. Right, so again, using the two-piece model, we can rearrange this, again, using the friction factor and Reynolds number, and we get these equations here, which these should look familiar based on chapter 3. If we include the buffer region, then we can slightly adjust this value to here, because now the thickness of the laminar sublayer occurs at 5 instead of 11.6, so this gets reduced a little bit. And basically what it says is that the laminar sublayer, if you follow this equation here, the thickness of the laminar sublayer, or delta, it basically decreases almost, not quite, but almost proportionally with Reynolds number. I mean, this is to the 7/8, so not quite proportionally. But it decreases proportionally. So as Reynolds number increases, it means the thickness of your laminar sublayer decreases. So as you get more and more turbulent, that laminar sublayer gets thinner and thinner and thinner. And actually, and you'll see this when we solve the problems, the thickness of the laminar sublayer is actually a very, very thin region of the total flow. So most of the flow is this sort of turbulent core with these big eddies and swirls and whirls, and then a very, very thin region of the laminar sublayer. However, as mentioned before, that thin region of laminar sublayer really dictates a lot of the transport properties in different chemical engineering applications. And so again, this one up here is two-piece model, no buffer region, three-piece model with a buffer region. Okay, so we'll finish up the rest of the video by describing and showing how we work with these different equations. And hopefully this makes a lot more sense once we see it in action here. So this is an example of a problem here. So we have a fluid. We're given a density, 1,500 kilograms per meters cubed, a viscosity, 0.03 kilograms per meter seconds. And this fluid is going to fall down through a vertical hydraulically smooth pipe. So this pipe's going up and down, and this fluid is just falling down this pipe. The pipe is 2.5 centimeters in diameter, so not super large. And we're going to be using the universal velocity profile equations to answer the following questions about the system. The first is calculate the shear wall stress. So what's the shear wall stress happening on the pipe walls? And then part B, what is the thickness of the laminar sublayer in this system? So let's go ahead and work on this. So the first part, calculate the wall shear stress. So the wall shear stress, which is going to be newtons per meter squared, we're going to calculate that by first starting with the force balance. So the sum of the forces are going to be equal to 0. And now we have to figure out, okay, what are the forces acting on the wall here? Well, you're going to have the shear stress at the wall times the area of the wall that the fluid's sort of interacting with. So it's going to be the inside surface area of the pipe, and then the shear stress at the wall, of the wall of the pipe. Now, what's the other side of the force equation? What's causing the fluid to fall? Well, it's going to just basically be gravity. So it's the mass of the fluid times gravity. That's what's pulling the liquid down. And then you can think of the shear stress as sort of resisting that flow going the other direction. Both of those are going to balance to 0. All right, so let's rearrange this equation a little bit. Let's plug some things in. So if we look at the area of the wall here, we can turn this into pi times the diameter, right? That's basically the circumference of the pipe, pi times the diameter, and then times the length of the pipe that the fluid's flowing down. So this is going to give you the inside area of the pipe times the length of the pipe. That'll give you the full area. You can imagine the pipe, if you were to take it and cut it down the middle and open it up, it would be your length times your width. Your length would be here, and your width here would be the circumference of the circle. So that's the wall stress here. If we look here at the gravity term, we don't want to necessarily deal with mass. We want to deal with volumes, volumetric flow rates, things like that. And so we'll convert mass here to just density times volume times gravity. So we just kind of converted this equation a little bit here. Next step, we're going to move this term over, and we're going to turn volume into diameters, because we have diameter on this side. So the volume now is going to be, just like this was a circumference times the length, volume is now going to be the cross-sectional area times the length. So the cross-sectional area is going to be diameter over 2, or radius, squared times pi times the length of the pipe. So we just converted here volume into this, and then moved this over to the right side of the equation. You look, there's a lot of terms that are on both sides of the equation, so we can go ahead and cross those out. So we can cross out pi, we can cross out the length, we can cross out one of the diameters, and then we can, we basically have the shear stress of the wall is equal to rho times gravity times the diameter of the pipe, all divided by 4. The 4 comes from this, 2 squared here. If you plug in the values that were given, density was 1500, I believe, and the diameter was 2.5 centimeters. You plug all this in, you'd obviously need to convert the centimeters into meters. You'd get 91.79 pascals of the shear stress of the wall here. Okay. The second part of the question was, what is the thickness of the laminar sublayer? So this is really saying, okay, you're going to have the fluids flowing down the middle. You're going to have a turbulent core that's just going to be doing all the most of the mixing down the middle of the pipe, but there's going to be a very thin laminar sublayer that exists right up against the wall. I keep saying it, but it really is important. In a lot of the transport processes in chemical engineering, this laminar sublayer, while it's very thin, really does control most of the transport properties in the system. So imagine this pipe, this horizontal pipe, was a heat exchanger. Most of the resistance of the heat going from the wall of the pipe into the fluid is going to happen because of this laminar sublayer. So even though it's thin, it's very, very important that we analyze how thin is it, how thick is it, for later transport processes. So how do we get the thickness of the laminar sublayer? Well, we're going to look at the equations we had before, these universal velocity profile equations. So laminar sublayer, this is going to occur. The laminar sublayer happens when y, the dimensionless distance, is 5 or lower. So anything less than 5 is going to be the laminar sublayer. And we're using the three-piece model here. So that means when y plus is 0, when y plus is 1, when y plus is 2, and everything in between, you're going to be in the laminar sublayer, all the way up until your dimensionless distance is 5. So we're going to say, okay, from 0 to 5, we're laminar, in the laminar sublayer. So let's calculate. We know that the boundary between the laminar sublayer is going to be when y plus equals 5. So let's set y plus equal to 5, and we're going to now convert this into real distance. And this is how we do this. Remember, we had our dimensionless distance is equal to our real distance from the wall times our friction velocity here times our kinematic viscosity right here. So we want to solve for y. So we can just rearrange this equation, right? We move y, we move this here over here, we move kinematic viscosity up here, and we rearrange this equation to get the actual distance, the actual thickness is equal to dimensionless thickness, kinematic viscosity, friction velocity here. So we can go ahead and plug in 5 right up here. We plug in our shear stress, our wall shear stress here. We were given our density, we were given our kinematic viscosity, which is just our regular viscosity mu divided by density. And we get, when we plug all that in and calculate for your real distance, you get this value here, 4 times 10 to the negative 4 meters. So you can see very, very thin. The entire pipe is 2.5 centimeters. So the actual thickness, so you think relative to the entire diameter of the pipe, again, 2.5 centimeters, the actual boundary layer, laminar sublayer here is 10 to the negative 4th meters. So less than a millimeter. We're in like the hundreds of micrometer range here. So very, very thin. Now, if you're going to use the two-piece model, how would this change? Well, the two-piece model, we just have a different boundary. We no longer have the transition region. So our limit here, instead of being 5, is now 11.6. So that's how you'd work with a two-piece model versus the three-piece model. Okay, so this is how, hopefully this makes a bit more sense. This is how you use the equations in the dimensionless form, but eventually you back out the real distances, and we'll see in the next example, the real velocities using this relationship here. Okay, so the last problem here we're going to talk about, comes from problem 9.9 in, again, the textbook that we used for the undergraduate class, and this will be part B of problem 9.9. And so it looks very similar, but water flows through a hydraulically smooth 5 centimeter diameter pipe under a pressure gradient of 14,000 newtons per meters cubed. So that's the driving force to be this pressure gradient pushing the fluid through. Find the wall shear stress, the mean velocity, the Reynolds number, the thickness, so that's a delta, the thickness of the laminar subregion, and the velocity of the junction between the laminar sublayer and the buffer region. So we're going to use a three-piece model again. So we're going to find all of these things. So let's first start off with the first part. Oops, sorry, wrong way. So wall shear stress, this is the first part. So how are we going to calculate the wall shear stress? Well, if you go back to one of the earlier slides that I presented, we had early on in a lot of the derivation, we mentioned that for a pipe, the wall shear stress is going to be radius over 2, and then the pressure drop here. Well, the radius of the pipe, we also call the full radius, is just going to be A. This is another value we often use for the entire radius. So the full radius of the pipe divided by 2 is equal to the pressure drop here. We were given all of these things. So radius of the pipe, the diameter of the pipe was 5 centimeters. So the radius is going to be that divided by 2. So we have 0.025 meters divided by 2. We plug in our pressure drop here, and we get the wall shear stress right here. Why is it important that we calculate the wall shear stress? Well, if you remember that value, that friction velocity, the shear stress of the wall over density, that was the key to unlocking the dimensionless numbers. So we need this to calculate the friction velocity and go back and forth between the dimensionless parameters. Okay, so we'll come back to that. The second thing that I asked here was to calculate the mean velocity. So if you remember the previous slides, we had two different equations. One was for Vz and one was for the mean velocity, Vzm. So we're going to use the dimensionless Vzm, which is 2.5 natural log of A plus the full radius of the pipe plus 1.75. The other one was Y plus, and then this has 5.5. So again, keep that in mind. There's a VZ and there's VZM. So mean velocity is VZM. So we're going to use this equation here. So the mean velocity, and just like Y, this should look very similar to the last slide. Just like Y, before we had Y plus equals Y, friction velocity, kinematic viscosity. Now we just substitute the Y's for A's, which is the full distance of the pipe. So dimensionless distance, the radius of the pipe is equal to actual radius of the pipe, friction velocity, kinematic viscosity. So again, this I mentioned before, this is why tau is so important. It helps unlock, it's the key to unlock going from dimensionless distance to actual distance and dimensionless velocity to actual velocity. So we can calculate here our friction velocity, which is just 175 right here, that's up here, the shear stress of the wall, divided by the density, because it's water, so it's 1,000, square root, we're gonna get this value here. And this should be meters per second. Now we can use this value here, plug it in to this equation, and we get our dimensionless distance is 2.5, that's the A, our radius of the pipe, times, this is our friction velocity, divided by our kinematic viscosity, which is the viscosity divided by density here, and we get A plus is 10,500. So it's very turbulent in the center of the pipe. If you remember the cutoff for the three-piece model, when you transitioned to the sort of turbulent center, was anything greater than 30. So this is much larger than 30. So we're definitely turbulent down the center of the pipe. It's usually nice to kind of look at these numbers and make sure that you're on the right track. So we're definitely on the right track to use this equation here. Okay, so now we have our A plus, we can plug it into this equation up here. So we plug in A plus right up here. That gives us 2.5 natural log times our A plus 1.75, and we get our dimensionless mean velocity is 24.9. And dimensionless, there's no units here. And now, again, we use our friction velocity as the key to go between our dimensionless mean velocity and our actual mean velocity. So we rearrange the equation to solve for our actual mean velocity, which is here. So it's just our dimensionless mean velocity times our friction velocity here. If you do that, you get 10.4 meters per second. That's our mean velocity of the pipe. So hopefully this makes sense how we don't know, we didn't know what our dimensionless distances were. So we used the friction velocity here to go from real distance, real radius, into dimensionless radius, and then using dimensionless radius to get dimensionless mean velocity. And then once we get dimensionless mean velocity, we can go back out into real mean velocity. That's kind of how these universal equations work. Okay, the next part of the question asks for what is the Reynolds number? Well, Reynolds number should be equal to, this is an equation that you have had since the beginning of these fluid mechanics notes and lectures, which is just our density times our mean velocity times the diameter of the pipe, all divided by the viscosity. So you plug all that in, you get this Reynolds number 5.20 times 10 to the 5. Again, very turbulent, that should make sense. This is another one of those checks. If you plug this in, you get a Reynolds number less than 2,000. That should send out some red flags. As if you remember back in the pipe equations, anything less than 2,000 is laminar, 2,000 to 4,000 is this transition region. Anything greater than 4,000 should be turbulent flow in a pipe. Well, we know it's turbulent. That was our assumption. That's what our numbers were giving us. And now you can see here that yes, indeed, we are turbulent. Okay, what's the laminar sublayer thickness? So again, we're doing the two-piece model, which means the laminar sublayer thickness happens when the dimensionless distance from the wall of the pipe is 5. So this is the definition of dimensionless distance equal to 5. So now we just use this equation and we rearrange and we solve for y here, real distance. If you rearrange, you basically get friction velocity, kinematic viscosity, all the same stuff. You plug it in and you get this value here. The laminar sublayer thickness goes from the wall of the pipe and only goes up 1.2 times 10 to the negative 5 meters. So again, we're in like the micron range. So very, very, very thin laminar sublayer. If we're using the three-piece model, we'd plug in 11.6 here instead of 5. That would be the thickness of the laminar sublayer. All right. And then the last thing it asked for was what was the velocity at the junction between the laminar sublayer and the sort of, in this case, it's a three-piece model, so it would be the velocity at the junction between the laminar sublayer and the buffer region. So again, when we're in the laminar sublayer, Vz equals y plus. And so we're going to say if Vz equals y plus and y plus at the junction is equal to 5, that means at the junction, our Vz plus our dimensionless velocity is equal to 5. So we use this definition of dimensionless velocity. Again, real velocity, dimensionless velocity. So we go here, we have Vz equals our dimensionless velocity. We plug in, sorry, this should be Vz, not Vzm, apologize. So we plug in 5 here, friction velocity, and we get 2.09 at the buffer region, at the boundary between the laminar sublayer and the buffer region. And that should make sense because in the last one we calculated that the mean velocity or the velocity of the whole pipe is 10.4, I believe. And so the velocity in the laminar sublayer should be much lower, and it is indeed much lower. Now, if we were going to use the two-piece model, again, this transition here, we'd get rid of the buffer region, and this transition here would happen at 11.6. So you'd plug in 11.6 here, and that would be the velocity using the two-piece model. So hopefully you guys see, so we kind of started the video going over a lot of really sort of derivations of how we go from Prandtl mixing length and all these assumptions about turbulent and Reynolds stresses that eventually allowed us to derive these dimensionless quantities. But in practice, we don't really go over all those derivations. Once we know these definitions, we just use these definitions and use these dimensionless parameters to go back and forth between the real values, go into dimensionless values, so we can use these values here. You know, in the laminar subregion, we get y plus and Vz plus equals 5. In the turbulent area, when y is greater than 30 or greater than 11.6 in the two-piece model, we have another set of parameters that says Vz equals 2.5 natural log of y plus 5.5, and that allows us again to calculate dimensionless velocity and then go back into real velocity. So hopefully you see now how you can analyze turbulence and analyze the laminar sublayer using these dimensionless equations, and hopefully get a flavor for how complicated turbulence is that requires us to do this, in contrast to the laminar flow where we could sort of solve these analytically and directly. And so this will hopefully prepare you now for some of the other transport classes where understanding these mixing lengths, understanding these boundary layers thicknesses will help you analyze the transport through these boundary layers and through into the turbulent region where a lot of the mixing happens. Thanks, and good luck on your next videos.